Good afternoon, everybody, and welcome to webinar number 4 of our climate change analysis using GIS tools. I hope that you've enjoyed the previous webinar modules and have had a chance to do the exercises. If you have not, today we'll be discussing to create a regional climate model and using extreme and creating the importance of extreme events indices. Again, we will be discussing the benefits of an ensemble analysis, how to create a regional climate model ensemble using GIS, as well as discussing the importance of extreme events indices and applications, looking at the ones we developed under RICCAR and how it could potentially be used for analysis that you may be conducting at your local level. So with that, we'll start getting into ensembles. So again, I know we've been discussing the 3 GCM, the global climate models that have been used for RICCAR. Again, they are CNRM CM5, EC Earth, and GFDL ESM2M. And as seen on the slide, you can see the different specifications describing these 3 climate models. The GCM resolution is the resolution of the whole model, the global climate model itself. And again, we've downscaled to 50 kilometer or 0.044 degrees, as well as 25 kilometer or 0.022 degrees. We downscaled these 3 climate models using the RCA4 model, which was developed by SMHI. And one point I want to clarify, I've often had users come to me and want to do even further downscaling, want to take the RICCAR data and use a method like interpolation, or what you may know as kriging, which is geostatistical analysis in GIS, maybe Krieg with another parameter such as elevation. This is not downscaling. Downscaling itself is a highly intensive dynamic process using a model. It is not looking at kriging or other methods that you might use in GIS. So there's definitely a difference. So if you are trying to downscale further using one of these methods like kriging or interpolation, that is incorrect. However, if you want to do kriging of observed data, if you have meteorological observations that you've observed and want to do a comparative assessment between the observed data versus our model data, you can do that. So you can, if you want to learn a little bit more about kriging, you can send me a message offline and I'll be happy to assist. But again, I just want to emphasize there is a difference. So do not downscale further the models that we have provided to you. So if we look at the differences in model outputs, for example, if we look at here are differences in mean seasonal temperature for June, July, and August over an observed period from 1980 to 2004. The maps, you can see some evidence and differences in these 3 maps. For example, if we look at Northern Africa, we can see, for example, in the CRNM model, it's a little bit warmer compared to EC Earth, which is a little cooler. And then it's about somewhere in the middle for the GFDL ESM2M model. Similarly, if we were to look at sub-Saharan Africa, we can see it's, really, really warm in GFDL, ESM, relatively cooler in EC Earth, and then somewhere in the middle for SIA and RM CM5. If we were to look at the winter months, there are differences. For example, again, in sub-Saharan Africa, this time the CNRM model is showing warmer temperatures. In terms of precipitation, precipitation is harder to model because of the high variability in precipitation. It's not as easy to model as temperature is. But there are evidence of differences in the models. If we were to look over the Tigris-Euphrates, it's a little bit, smaller to tell, a little bit more difficult to tell. You could see here a little more yellow than blue, and these areas are primarily blue, indicating lower amounts of precipitation during the summer months. Here in this Sahel area, you can see it's a little bluer here in the GFDL model, indicating differences in precipitation during the summer months. During the winter season, we can look at more evidence of differences, particularly in the Horn of Africa seen here. It's primarily in the yellows here, indicating higher precipitation, whereas it's more blue for the EC Earth and the GFDL model. The reason why I want to emphasize all these is because sometimes I am asked which model is best to use. And the answer is there is no best model. The best solution is to create an ensemble and present the results as a mean. So beginning in the 1990s, the differences in RCM models became apparent. And it became apparent it was difficult to assess systematic model behaviors and interpret the results. And it was a call to use the same simulation protocol against all models to better characterize in climate change and minimize the uncertainties. And we do this by creating an ensemble. It is recommended to use the largest model ensemble for application and evaluation of modeling outputs. For RICCAR, we have 3 model members, and the general consensus is 3 is the absolute minimum. But if you happen to have data that contains more model ensemble model members, you can certainly do so. However, you should not mix and match different RCP scenarios. For example, if you happen to have RCP 4.5 data and RCP 8.5 data, you cannot mix those, even if they're different models for an ensemble. You should have all of them be the same RCP scenario. However, you can mix and match if you happen to have differences in RCMs. For RICCAR, we only have data using the RCA4 RCM, but other data sets might have different institutes that may have conducted the downscaling using their own regional climate models. So those are perfectly acceptable to use. And again, climate modeling, the intent of climate modeling is not to assess over short term. There may be little nuances in the model that might not completely tell an accurate story. So an ensemble mean should be conducted over an extended period. One recommendation is 30 years in RICCAR, and which is becoming quite common to use, is a 20-year period. As I mentioned, you can use more than 3 members, certainly, and our upcoming Maastricht domain will have 6 members that could be potentially be used. The driving GCMs are to be determined at this point. One of them will be EC Earth, and the RCM to be used will be the Aladdin model, this is an adaptation of the Aladdin model developed by SMHI. They'll be used for the nesting RCM from the model. So again, those results we expect in early 2021 to be available. So to clarify, again, multi-model ensembles can have different GCMs and RCMs. They should be the same climate scenario or RCP. They should have the same spatial and temporal resolution. So you should not mix 25-kilometer data with 50-kilometer data. And you should not mix daily data with monthly data. They all should be consistently the same to have to minimize differences in modeling approaches. The modeling domain should be the same. Next week, we're going to be looking at different Cortex domains. So you should not mix data from the African domain. If you're looking in the Northern Africa region, mix data from the African domain with mixing data from the Arab domain. All of your ensemble members should be from the same domain to have the same boundary conditions established and other assumptions be the same. And then you should not mix bias corrected data with raw RCM outputs. They should all have the same assumption in that regard. Again, so next week we'll be looking at Cortex data, which will be raw RCM outputs. And again, so you should not mix the bias-corrected RICCAR data with the raw RCM outputs, which you may obtain from Cortex. So available on our regional knowledge hub, which we'll be discussing next week, we have, which has also been published in our RICCAR reports. We have present the data as ensembles. If you look at our maps, they represent an ensemble, which will have the 3 models that is shown here. And with the 2 different scenarios, RCP 4.5 and RCP 8.5. And in the RICCAR reports, we show the reference period, mid-century, which is 2046 to 2065, and end century, which is from 2081 to 2100. On our regional knowledge hub, we also introduced the near century data. Near century could be a little bit controversial because if you look at the time frame, we are currently in a near century. So, it could be argued that it's more indicative of climate variability rather than climate change. But there is definitely a request for those data sets available on our knowledge hub. So that's why we created near century data. But again, in our report, we only have these 3 periods available. And these time periods are established in accordance with IPCC in their 5th assessment report, which is how we determined these time periods. So if you want to have other ensembles, you will have to create your own, which is the point of our discussion today. You may want to have a seasonal data set. You may want to have a different time period. It's becoming more common to report 2030 data based on the 2030 agenda. 2030 can be described as a 20-year period from 2021 to 2040. So we do not have those data sets readily available. We can assist, but you may want to develop your own for different reasons. So we'll look over how to do this in GIS. It is a multi-step process. It can be a time-consuming one, but as you become adept at doing so, you'll become faster and faster, and it will help facilitate the process. So the first step we will do is to extract each raster time slice. So we do this again by making a net CDF raster layer, and I know you've all become masters at doing this by now. So once we have done that, we look at the layer properties. You right click on the layer in GIS. You can open up the properties. And if you need a little refresher, you can go back to module 2 if you need a little reminder of how to do this. And what we will do is change the band dimension marked as time. And then we will select the band dimension time, and this where it is, you can see originally the time here, which is January 1st, 2046. The band dimension will go blank. I did have a question this past week from a participant who said they were not able to change the time and their time was marked differently. If you're having trouble with time in your NetCDF raster layer, it is perhaps maybe you are more commonly working in the French language and using a comma as to indicate decimal positions rather than a point. So what you should do in that instance, if you have trouble with the time will only be read in NetCDFs and in GIS by using a decimal point, not a comma. So you'll have to change your regional settings to account for that in your computer settings. And hopefully that will work if you're having trouble with that. So again, it must be a decimal point, not a comma in your regional settings for the decimal. And then you will save as a raster layer. You will right click on your raster layer and say, on your raster in your table of contents, and save as a raster layer, and you could utilize to further. And here's where to find that in both the Arabic and as well as the French versions of GIS. To extract each time slice, there's a tool that has been developed by ESRI, and here is the link. It describes these steps in detail, and as well as gives you, you can't quite see it here, but it gives you a link to download the tool to use in GIS. We open that tool, that NetCDF to raster tool, in Arc Catalog, not directly in ArcMap. So you will find it where you have saved it. You may have saved it on your computer hard drive under GIS. It might have done that automatically, or you may have saved it into a user specified location. You'll find the tool, it'll tend to nest itself in kind of some subdirectories as shown. So you will wind up having to open all these little subdirectories, and you will click on this, it'll look like a scroll sign, and then the tool will be located at NetCDF time slice export to open the tool. Once you open the tool, it'll have these two fields. You'll input your raster layer wherever you have saved it, and select your output folder, which is also user defined. I recommend that you separate a output folder for each individual NetCDF file, otherwise the files might not run, or it will overwrite one another. So it's recommended to name your output folder with a unique name, perhaps with the climate parameter, with the year, as well as the appropriate driving GCM. So again, we input that layer file we had saved the previous step in step 1C, and then define our output folder. And once that's completed, it will execute. If you find that you only have one band layer in your results, it's because you did not select the time dimension previously when you saved your layer file. Only the initial first time slice from that NetCDF will have been saved, and thus you'll only have one band. So if you've done it correctly, you'll see The result being 365 bands for most years. It would be 366 bands for those leap years, the years that have February 29. For the extreme climate indices, there should be 150 bands representing the years from 1951 to 2100. So once we have done that, we will start to calculate our annual or seasonal projections. So this will be the first step for one model, one RCP scenario. And you'll repeat these steps as you go through subsequent years and subsequent models. So we do this by opening up our Spatial Analyst tools. A couple of you have mentioned that you do not have access to these tools. You might not have the licensing. If that's the case, I could potentially provide you with a link. There's a trial version from ESRI that's available they could potentially use, or otherwise we can assist with looking into alternate solutions if you do not have a licensing for using the Spatial Analyst tools. So under Spatial Analyst tools, you under local, we will select cell statistics, and they will help us calculate the mean or sum, and we'll look at the reasons why to be able to calculate annual or seasonal projections. Here is that same tool and where to find it on both the Arabic and the French versions of GIS. So once you open the tool, the fields look as follow. So what we do is first select our raster files we want to calculate, our input rasters. So if we open the drop-down box or a folder, it will look something similar to this. If you notice, each band is not necessarily listed in chronological order. You'll see band 1 followed by band number 10. Which can pose some challenges if you want to calculate monthly data, and we'll look at how to kind of overcome this in a moment. Each of these bands correspond to dates of the year, and they're automatically named. So band 1 to band 31 is January 1st through January 31st, and therefore. So here's the band names corresponding to the calendar days in normal years on the left, and then for leap years, years that have February 29 here on the right. So again, so if you want to select years, different days for different years, for different months, it may be a challenge because otherwise you have to pick and choose individually the bands, which, you know, here's band number 2 for January 2nd, which is not immediately next to the preceding day of January 1st and the subsequent day of January 3rd. So a way to overcome this is open up your Explorer and just drag and drop the files. Under Explorer, they will be listed in chronological order. So you can just drag and drop all these files. Now, one thing to note is the files will be marked in they'll be marked, there'll be multiple files that'll be marked. You need to select all of them to drag and drop. Once you do this, it will say that some files are invalid. Don't worry about that. You can disregard that message. Not all files will be used when you drag and drop. So, you know, and again, even so, it's easier just to select them all and then drag them, drop them all, even though all files will not necessarily be used to use this tool. From there, you select your output raster. You could either leave the default temporarily or be user-defined. I generally recommend a user-defined name to be able to find the result later. And then we select our output raster statistic. So there's definite options you can select from, and the default is mean, but and here's a close-up of the overlay statistic. The default is mean, but there are different other options you can select for them if you are interested. So mean we would use for temperature, because temperature data is not time dependent. However, it is more common to report precipitation in millimeters per month. So if we selected mean for precipitation, it would mean our results would be reported in millimeters per day, because our precipitation data is daily. So in that case, it is more common to report precipitation data in either millimeters per month or millimeters per year. And in that case, instead of mean, we would select sum before we proceed to calculate the monthly or annual precipitation. And once we have done that, for example, here is the monthly precipitation we have calculated, and then we then select mean to calculate the average monthly rainfall for the year, as I have highlighted here. So this week's exercise, if you look at your data set, I provided a netcdf file. It's an extracted file again. It is EC Earth data based on RCP 8.5 for the year 2030. You will do all the steps. You will calculate using that netcdf to raster tool. You will extract all of the daily raster files. You will then sum the monthly precipitation and then calculate the mean monthly precipitation. And here is the results, if you've done it all correctly, what you will find if you do all the steps properly. I've added the background shapefile just for your spatial reference, but that's certainly not necessary in order to conduct the exercise. So if you have any questions with conducting the exercise, please feel free to contact me and I'll be happy to assist you. So that's this week's exercise. So once we have done that, we repeat these steps for every single netcdf file in the ensemble. So we have, we might have 20 years of results for each individual GCM. And then we will calculate the mean of all of those entire results, as I've tried to illustrate here. So again, it's a multi-step, multi-iterative process. It can be time consuming, but once you get more and more comfortable with it, you can kind of, it will go faster and faster. So if you have any trouble, again, I can be happy to assist you. Now, typically, we do not report these results on their own. We will, if you calculate the data for the year 2030, you'll report the absolute value for a 2030. However, it is quite often they will report to a reference period. So for example, if we look at one of the maps that is in our RICCAR report, you will see here are the results for 2046 to 2065 or mid-century, and it compares back to this reference period, which is from 1986 to 2005. Similarly, if we were to look at end century from 2081 to 2100, it again, it reflects a change compared to this reference period. And here is the quantitative amount for the change. This is to help highlight the degree of climate change that is being, which is to be expected. So to do this, to compare to a reference period, we again open our Spatial Analyst tools. And under Spatial Analyst tools, there is a tool called, there's a set of tools called Map Algebra. And under there is a tool called the Raster Calculator. The Raster Calculator we'll be using a lot, particularly in webinar module 6. So this will be our initial exposure, because when we use when we get to vulnerability assessments, there'll be much more complicated calculations we'll be doing. So this will be a good introduction to the Raster Calculator if you have not used it before. Here's that same tool in the Arabic and French versions of GIS, and the tool will follow similar steps for the different languages. So if you open the tool, it will automatically show all of your layer files that are currently open in your ArcMap project. You cannot add them directly into the Raster Calculator like you would for other tools. It already has to be open in your ArcMap project. So you'll select the layers of interest, for example, precipitation for 2030, your precipitation for reference period, and you simply subtract. Here are your different computational operators you could use to calculate the difference. And then you specify a user-defined output raster to define your change in value. So with that, that is a summary of how we create an ensemble in GIS. And from there, we will move into creating extreme climate indices. Again, I provided you the exercises described on the previous slide. Feel free to conduct it as your time allows. If you have any questions, if you have difficulty downloading the MakeNet CDF raster layer, the MakeNet CDF extract tool, or difficulty finding it in our catalog, please feel free to send me a screenshot and I will be happy to assist you. So with that, let's look at extreme climate indices. These extreme climate indices were defined by a team known as the Expert Team on Climate Change Detection and Indices, otherwise known as ETCCDI. They've standardized kind of mechanisms to look at different indices. And I've defined all of these indices, if you look at your notes, to kind of give you a more description of what each of these indices mean. Some of these obviously will not necessarily have applicability to our region, but some of them very, very much do. So I have highlighted the indices that we've developed under RICCAR. They're all highlighted with the box in red. And as well for RICCAR, as we've discussed earlier, we increased the threshold. I mean, originally the official indice for summer days is defined as temperature above number of days with a temperature exceeding 25 degrees. However, for RICCAR, we developed a couple of our own indices, which are SU35 and SU40. But otherwise, we used the remaining indices you have seen highlighted, and as again, the definitions are defined below in your notes. So why are these extreme climate indices important? I want to highlight these because quite often I've seen people use studies and all they are concerned about are the precipitation and temperature data. And while these parameters are definitely important, I don't want to, minimize their significance in any way, they don't always tell the entire story. And so, for example, if we look in the upper graphic, we look at precipitation, for example, here in Oman and Yemen. We see a general decline in precipitation for mid-century RCP 8.5, except for this little corner here, which is showing increasing precipitation. But the lower graphic is SDII, which is a parameter that kind of describes intensity of precipitation. So although generally precipitation is declining, when it does occur, we could see that it is increasing in intensity. This is important if we were to look at flooding, flash flooding, might be important when we're looking at infrastructure. So So this is just one example of how an extreme climate index can be important to kind of have a further assessment of what is exactly happening in your region of interest. Here's a look at temperature. So the top graphic is mean change in temperature for mid-century for RCP 8.5, as seen here, and we're looking here in the central Arabian Peninsula, and in a little bit of a modest temperature increase, in the range of about 1.5 to 2 degrees. But at the same token, if we look at that SU40 index, that number of days that exceed 40 degrees, we can see a dramatic increase. So, and this kind of raises concerns for heat waves. It raises concerns about heat exhaustion. I mean, number of days above 40 degrees is quite concerning for heat-related illnesses. So this is why we raise importance of looking at temperature indices. So in summary, the monthly or annual averages can mask out important information such as extremes, which can be very important for sectoral applications. And these extreme climate indices can help with mitigation, adaptation, risk reduction, and policy planning. So again, I want to stress the importance of extreme climate indices. I've received many times that I've gotten requests for data, and only one requester thus far has requested data on extreme climate indices. So I hope that through this webinar series, I encourage more and more of you to use extreme climate indices. So here's some potential applications you may consider for using extreme temperature climate indices. Looking at heat wave duration, perhaps looking at fire risk, looking at heat-related illnesses, looking at agricultural productivity decline, looking at heat stress not only on people, but looking at heat stress on livestock. And there are probably many other applications that I've not listed here that you may want to consider. In terms of precipitation, all the different precipitation climate indices, they're useful for looking at rainfall and flash flood. If we're looking at, although in the previous example, that precipitation overall on an annual basis is declining, but when it does happen, the rainfall is much more intense. That gives rise to flash flood. On the flip side, these indices might tell an indication of drought, whether it be agricultural drought or impact deforestation. They could also impact, again, back with flood, if you look at urbanization and increased flood risk, looking at infrastructure, are your roadway bridges and culverts sized appropriately? Are they at risk of flood? These different climate indices can tell about that. And lastly, again, on the flip side, if we look at these extreme precipitation indices, they can be indicative of water scarcity. So with that, I hope you've been asking questions to my colleague Joelle Amer. She will relay any questions that you have received, and I'll be happy to answer. Thank you.
Marlene, we have no questions at this point.
Okay, well, I thank you. Again, I'm sorry this went a little quickly. If you again any questions, I've been happy to receive all your questions. I know a few of you have been sending questions, either troubles with software or checks questions about the exercise. And I've already been receiving requests for data for applications that you may want to conduct at your local level. So I welcome all of these questions, and I'm very happy to assist. So Thank you very much.